All right, let's start again. So welcome back. And our next speaker is Luca Reggio from the UCL, who's going to talk about arboreal categories and homomorphism preservation theorem. Luca, please take it away.
Thank you. So the topic for this talk is a categorical approach to homomorphism preservation theorems, which is a family of results in logic. And the categorical approach is based on the notion of arboreal category. And in order to motivate this notion, I should first tell you a little bit about game components. This is a comonatic approach to finite model theory, and the idea then is that arboreal categories provide a sort of axiomatization for this framework. And then in the last part of the talk, I'll say a bit about applying this axiomatic framework to study homomorphism preservation theorems in logic. Right, so the idea behind game components is that model comparison games in model theory should be seen as semantic constructions in their own right. So these are typically two-player games, that's spoiler and duplicator. And spoiler is trying to show that two structures are different, and duplicator is trying to show that they're similar. The meaning of different and similar is made precise if you fix a logic fragment, L. So think of some set of first-order sentences. And then to such logic fragment L, you can associate an equivalence relation which says that A is L equivalent to B if and only if A and B satisfy the same sentences from L. And if L is all of first-order sentences, then this is simply elementary equivalence. And then we have the Kizler-Schiller theorem, which gives a semantic characterization of this syntactically defined logical equivalence. The point is that for finite structures, elementary equivalence collapses to isomorphism. So this is not interesting. If you're interested in finite structures, you would typically look at proper fragments of first-order logic, and typically these are defined by bounding some number of resources. So you could bound the number of variables, or as we see, the quantifier rank and so forth. In that case, you don't have ultra powers and a sort of analog to the Kizler-Schiller theorem. And that's where model comparison games become important. As we see, this categorical framework gives us not only a structural approach to logical equivalences, but also perhaps more surprisingly to combinatorial parameters, which are very much studied in finite model theory. And I should stress here that although many results of interest for finite models, much of this framework applies uniformly to both finite and infinite structures. So you could see this talk as a sort of category theoretic view on what may be called resource-sensitive model theory, or perhaps model theory without compactness. So I'd like to recall one notion of game, of back and forth game, and this would be a sort of our running example throughout the talk. So typically we work with structures over a finite relational signature, so there are no function symbols, no constants. You could add the constants if you wanted to, essentially some causalized categories, but for the sake of simplicity, I'll just work with purely relational signatures. And then there's a classical notion of back and forth Ehrenfeucht-Fraissé game between structures A and B. And it goes as follows. In the ith round of the game, spoiler chooses either an element from the structure A or an element from the structure B, and duplicator responds by picking an element in the other structure. So after k rounds, you have a relation which is given by these pairs of elements which have been chosen, and duplicator wins after k rounds if this relation is a partial isomorphism between A and B. Explicitly, that means that these two conditions are satisfied. The first condition says that the relation is functional, and so it's a graph of some function. This function is injective. That's a right to left implication in item 1. It's also surjective by construction, and the second item says that this function is an isomorphism. So it preserves and reflects the relation symbols. Then this classical result by Ehrenfeucht-Fraissé makes the link between games and logic. So it says that for any two structures A and B, duplicator has a winning strategy in the K round back and forth Ehrenfeucht-Fraissé game, if and only if A and B satisfy the same sentences in first order logic with quantifier rank at most K. So you see here the resource parameter in the case of games is the number of rounds, K rounds, and at the level of logic that corresponds to the quantifier rank of sentences. And the quantifier rank of a sentence is the maximum number of nesting of quantifiers. So it's a way to measure the complexity of a sentence. Then there's also a variant of this game where spoiler only plays in one of the two structures, say in the structure A, and duplicator must respond in the other structure, in this case B. And the winning condition in this case is that the relation that we obtain is not the partial isomorphism anymore, but the partial homomorphism, which means that we only have left to right implications in these two conditions. And again, this corresponds to some logical equivalence, in this case relation, and the result is that duplicator has a winning strategy in this fourth only version of the game with K rounds, if and only if B satisfies all existential positive sentences with quantifier rank at most K satisfied by A. So existential positive in this case means that you do not use the negation symbol nor universal quantifiers in these sentences. Right, so this is for the link between games and logic. Now, with these ingredients, we'd like to sort of cook up a comonad. That's the idea. As I said before, the intuition is that we should see games as semantic constructions in their own right. More concretely, what this means is that you can consider the set of all plays in the fourth only version of the game, say played in a structure A, and you turn this set of possible plays into a structure itself for the same relational signature. And this is done in the following way. So we fix a relational structure A and consider the set EK of A of all non-empty lists of length at most K of elements from A. These are simply all the possible plays in A in the game where you have at most K rounds. And then right away, you can define a function from EK of A to A, which sends a sequence to its last element. Right? It's extracting the last move in the play. And then the crucial step is to lift the interpretation of the relations from A to EK of A. And that's done in the following way. So whenever you have a relation symbol R of arbitrary n, its interpretation in EK of A will consist of the tuples S1, Sn of sequences that satisfy the following two conditions. The first condition says that these sequences are pairwise comparable in the prefix order. And the second condition says that if you look only at the last elements in each of these sequences, these must be related in the structure A. So one thing that you get right away just from item 2 in this definition is that the functions epsilon A become homomorphisms. Right? They upgraded from simple functions to homomorphisms of sigma structures. So that's the first observation here. The second observation is that you can reconstruct the history of duplicators' answers in the following sense. So suppose you have a homomorphism F from EK of A to B. The idea is that if you take a sequence of elements from A, so that's an element of EK of A, this F will output a duplicator's answer, given that spoiler has played those elements in the sequence. But we can define a coextension of F, so F star from EK of A to EK of B, that takes a sequence A1, AJ, and it sends it to a sequence obtained by applying F to all the prefixes of the sequence. Right? So the first element F of A1, this will correspond to duplicator's answer in the first round, F of A1, A2 to duplicator's answer in the second round, and so forth. So you're kind of reconstructing the history of duplicator's answers. Now this data, which means this EK, which is assignment on objects of the category sigma structures and the homomorphisms, and this family of homomorphisms epsilon A and this coextension operation, these form a so-called comonad in Kleisli form. So you may be more familiar with the definition of comonad in terms of an endofunctor with a two natural transformations like co-unit and co-multiplication. This is an equivalent way of presenting a comonad. So what I'm omitting here is that in order to be a comonad in Kleisli form, there are some equations, I believe 3 of them, that should be satisfied. And they're very simple to state and very simple to verify in this case. And then it turns out that, well, EK is a functor on the category sigma structures. These epsilon A, they form the components of the co-unit, and you can define the co-multiplication by essentially taking the coextension of the identities, appropriate identities. And so this is what we call the Ehrenfeucht-Fraissé comonad. And I should point out here is that it's not a simple, just one comonad, it's actually a family of comonads. Because this works for any positive integer k, so this is really a family of comonads indexed by the source parameter k, which in this specific case is the number of rounds in the game. Once you have this definition of this Ehrenfeucht-Fraissé comonad, you can recover right away some logical relations. So if you want to recover preservation of existential positive sentences with quantifier rank at most k, that corresponds precisely to the homomorphism preorder in the Kleisli category for the comonad, in the sense that there exists a Kleisli morphism from A to B. So this would be a homomorphism from EK of A to B, if and only if B satisfies all the sentences in this logic fragment which are satisfied by A. And similarly, again, within the Kleisli category, you can look at isomorphism. What does isomorphism in the Kleisli category correspond to? That corresponds to equivalence in first-order logic with quantifier rank at most k, extended with so-called counting quantifiers. Right? That's the hash symbol. And these counting quantifiers, what they allow you to do is to say things like there exists at least an element satisfying a property. So this is pretty much all you can do if you work in the Kleisli category. But you may want to recover equivalence in all of F for K, that's the logic with quantifier rank and most K. It turns out that in order to do that, you need some more room. So you need to work in a larger category. You need to work in the category of all Eilenberg-Moore coalgebras for this comonad. And in that case, this equivalence is captured precisely by a certain notion of bisimilarity that I define in a few slides. But so this motivates the question of what are the coalgebras for this comonad? Can we understand them a bit better? And in fact, they emit a rather neat characterization. So the coalgebras, in this case, they can be described as follows. So they are essentially pairs. When the first component you have a sigma structure, and the second component you have a partial order. And then there are some conditions. So the first condition is that this partial order is actually a forest order of height at most k. And what that means is that if you fix any element in the structure A and you look at all the elements which are below it, then this is a chain of cardinality at most k. And then the important condition E here is that the forest order is compatible with the sigma structure, which means that whenever you have two elements which appear in a tuple of related elements, then they must belong to the same branch of the forest. And then the morphisms of coalgebras, they correspond precisely to the sigma homomorphisms, so the functions that preserve the relations that are also forest morphisms. What that means is that they are monotone maps that preserve the height of elements. And once you have this nice description, it's actually rather easy to prove this theorem. And the theorem says that a sigma structure A, so whenever you have a sigma structure A, the smallest integer k such that A admits a coalgebra structure for the comonad Ek coincides with the so-called tree depth of A. So this is a combinatorial parameter which was introduced for graphs first and then extended to relational structures. And it's really important in finite model theory. And it turns out here to correspond precisely to coalgebras for Ek. Okay, if you admit k to vary among the integers. All right, so this was a bit quick, but the main point here is that this template is not specific to Ek, but you can give similar analysis of other logical and combinatorial notions in a very similar way. So you could look at pebble games and the corresponding pebbling components. The idea in pebble games is that each of the two players has k pebbles, and they place in each round they place a pebble on an element of one of the two structures. And the idea here is that the pebble represents a variable, and placing the pebble on an element of one or two structures corresponds to interpreting that variable as that element. But when you write down a sentence, you can also reuse the same variables more than once, and that corresponds to the fact that they can move the pebble around. So what happens is that this game is actually an infinite game, because you can keep moving these pebbles around. So the resource parameter in this case is not the number of rounds anymore, it's rather the number of pebbles. And these games, they capture finite variable fragments of the study logic, and the corresponding combinatorial parameter is tree width. And again, you can capture these combinatorial parameters and the corresponding logic fragments using a certain notion of pebbling component. And you can do something similar for model logic and look at bisimulation games between Kripke structures and define a corresponding model component MK on the category of pointed Kripke structures. And this capture the level of logic model formulas with bounded model depth. So the model depth is the maximum number of nesting of modalities. And again, there's a corresponding combinatorial parameter and so forth. Many other examples of game components. So what I've said so far is basically contained in these two papers. So game components were introduced in 2017 by Abramsky, Davar, and Wang in this first paper. And here they only deal with the pebbling component corresponding to pebble games. And then the case of the Ehrenfeucht-Fraissé component and the model component that were introduced in a CSL 2018 paper by Abramsky and Shah. So what you see here, it's actually the journal version of that paper. Okay, so this was a very quick but necessary introduction to game components. Now, intuitively, Arboreal categories provide an axiomatization of the categories of coalgebras for game components. That's the main idea. And they're essentially based on the notion of a path. And okay, let's get to this. So the notion of a path is defined in terms of a good factorization system. So we start with a category C with some proper factorization system, QM. So what this means is that is an orthogonal factorization system in which the class of quotients, the Q morphisms, is contained in the class of epimorphisms, and the class of embeddings, the M morphisms, is contained in the class of monomorphisms. And then usually in category theory, we consider the poset of subobjects, so equivalence classes of monomorphisms. Now you can consider M subobjects, so equivalence classes of embeddings. And you define an object X in this category to be a path, provided that its poset of M subobjects is a finite chain. Right? So the definition only depends on the factorization system. And then the idea is that Arboreal categories are categories in which paths are well behaved. So to give you an example, if you look at coalgebras for Ek, those are some kind of forest ordered sigma structures, as I explained before. And if you take the factorization system to be given by the surjective morphisms on the one hand, and on the other hand, the embeddings are those morphisms that are embeddings qua sigma homomorphisms. Those would be the injective homomorphisms that also reflect the relation symbols. Then with respect to this factorization system, it turns out that the parts are precisely those objects in which the forest order is a linear order of height at most k. You could do the same thing by taking sigma to be the empty relational signature. So you're just talking about essentially forest here of height at most k, and then the parts would be chains with at most k elements. And an umbrella category is a category with a good factorization system. Again, a proper factorization system. Then there's a stability condition here, which essentially means that quotients are stable under pullbacks along embeddings that satisfy these four conditions. So the first one is just the existence of coproducts of small families of parts. The second one says that if you have three parts, P, Q, and Q prime, and two morphisms of this form, if the composite is a quotient, then the first one is a quotient. What you would get automatically is that the second one is a quotient, but you also require this, that the first one is a quotient. The third condition is perhaps the most important one, and it says that every object is the colimit in a sort of canonical way of its path embeddings. So path embedding is an embedding whose domain is a path. So you take any object X, you look at all embeddings whose domains are paths. This gives you a diagram, a cocone, and you require that this cocone is a colimit. So in a more precise way, what you're saying is that the inclusion of the full subcategory defined by the parts is dense. That's what it means. And then the last condition is that every path is connected. So now that's a very classical notion of connectedness in category theory, which says that an object is connected if the corresponding covariant home functor preserves coproducts. But that prevents the initial object from being connected, of course. What we do here is to slightly change this definition and simply require that whenever you have a morphism from a path to a coproduct of parts, then this would factor through some coproduct injection. So we're essentially replacing some bijective maps by surjective ones. Okay, but this is really a minor point. Examples, as you would expect, the category of coalgebras for the Ehrenfeucht-Fraissé comonad is an umbrella category, and similarly for the categories of coalgebras for the Pevin comonad and the model comonad. Another example is the category of forests. That's also an umbrella category. But one important thing is that whenever you have an umbrella category C, you always have a functor into the category of trees. And so how is this defined an object? So whenever you have an object X, you can look at the set of all path embeddings into X. That's naturally a subposet of the poset of embeddings into X. And it's in fact a non-empty tree. The interesting part is that every morphism in the above category is actually sent to a forest morphism between the associated trees. So by a tree, I simply mean a forest which has at most one root, one list element. So you always get this fount of parts from an above category into the category trees. And this allows you to reason in a sort of concrete way about objects in the above category. Then you can prove some nice facts about above categories. So just mention a few very quickly here. For instance, you can show that parts are closed under quotients and embeddings. You can show that between any two parts, there is at most one embedding. And then it turns out that the posets of embeddings in this category, they are actually perfect lattices. So they are lattices of downsets of certain posets, which are given by these forests here. Right, so there are some natural notions that you can define in above a category. For instance, you can generalize the notion of embedding to obtain a notion of pathwise embedding. If you have a morphism f from x to y in an above a category, you would say that f is a pathwise embedding if whenever you precompose it with some path embedding, the result is again a path embedding. Another important notion is that of openness. Say that F is open if it satisfies the following path lifting property. This says that if you have a commutative diagram, the outer diagram here, so P and Q are paths, and then you have 3 embeddings here, then there must be some diagonal filler in this diagram. So why the name path lifting property? Well, essentially, intuition is that this is saying that whenever you have a path of shape P in X, which can be extended to a path of shape Q in Y, then it can also be extended to a path of shape Q in X. That's essentially what it means. And this is a slight refinement of a classical notion of open map, which was introduced by Joyal, Nissen, and Viskel in 1993. It's a refinement because we required these 3 maps to be embeddings. And this actually, the notion of open map introduced here is actually a special case of the notion of open morphism in Topos theory. Okay, so now with these 2 ingredients, pathways embeddings and open morphisms, you can actually define a notion of bisimilarity in any Arboreal category. So objects X and Y are bisimilar if there exists a span of open pathways embeddings which connects them. What's interesting, I believe, is that this notion can be captured in terms of games abstractly in any Arboreal category. You can use the functor into the category trees to define a back and forth game between X and Y, while it's actually played on the trees associated with X and Y. And this game, if you instantiate it to the case of the coalgebras for the Ehrenfeucht-Fraissé component, you recover precisely the Ehrenfeucht-Fraissé game. If you do this for the pebbling component, you get pebble games and so forth. So this is an abstract notion of game which makes sense in any Arboreal category, and it generalizes all these concrete notions of game. And the theorem says that assuming that X and Y admit a product in the category, then they are bisimilar if and only if duplicator has a winning strategy in this game. I see. Right. If you remember, when I defined the Ehrenfeucht-Fraissé component, I said that it's actually a family of components because they were indexed by the positive integer k, and this aspect hasn't really been present in the picture so far. So we should somehow introduce resources into the picture. And this is done by considering resource index Arboreal categories. The idea is that you start with an Arboreal category C. Its full subcategory defined by the paths is CP. And then you say that C is resource indexed if for each K there is a full subcategory CPK of CP. So this is some collection of paths essentially, which is closed under embeddings, so downwards closed in a sense, such that these categories, they form an increasing chain. Okay, so you're choosing larger and larger classes of paths. And this chain of inclusions induces a corresponding tower of full subcategories CK of C. Right? The objects of CK are those which are generated by the paths in CPK. So those which are colimits of paths in CPK. And by the way, it turns out that these categories CK are also Arboreal categories. That's something that can be proved. And then what you're interested in is the notion of resource index above adjunction between some category E, okay, that's some base category, which typically is a category of sigma structures, but it could be anything for the moment. And if an adjunction between this category and the resource index above a category. So that's simply a family of adjunctions. Okay? So you have category CK, one for each positive integer K, and then you have one adjunction for each K. Okay, so in the concrete examples, CK could be, for instance, the category coalgebras for the Ehrenfeucht-Fraissé component CK. And then these adjunctions would be the canonical ones. So this RK would be the co-free coalgebra functor, and AK would be the forgetful functor. In that case, the adjunctions will be comonadic, but in general, we do not need this comonadicity assumption. So I dropped that completely. It's not in the picture anymore. We simply have a family of adjunctions. All right, so what you can do once you fix this family of adjunctions is to define some resource index relations on the base category E. So for instance, you can look at two objects A and B in the base category. And you say that there exists a K morphism from A to B if there exists a bona fide morphism from Rk of A to Rk of B. So the idea is that you have two objects in the base category, you apply the right adjoint functor, and then in this case, you look at the homomorphism preorder, right? That's what you're doing. And then similarly, you can look at whether these two objects are bisimilar in the Arboreal category, and that gives you a K bisimilarity relation on the base category. And you can do the same for isomorphism in the Arboreal category, and that gives you some notion of K isomorphism in the base category. Again, if you look at what this means in the case of the Ehrenfeucht-Fraissé component and the associated resource index above adjunction, then this K homomorphism relation coincides with preservation of existential positive sentences with quantifier rank at most K. K bisimilarity corresponds to equivalence in F of K, and K isomorphism to equivalence in F of K with counting quantifiers. And similarly for the other components. But this can be done abstractly whenever you have a resource index above adjunction. All right. So the last, let's say, 10 minutes, what I'd like to do is to try to explain to you how you can use this framework of above categories to study something concrete in logic, and more specifically to study homomorphism preservation theorems. So this is a family of results that relate the syntactic shape of a sentence with the semantic property of being preserved under some class of homomorphisms between structures. So what do we mean by preserved under homomorphisms? If you have a first order sentence phi, then this is preserved under homomorphisms if whenever you have a homomorphisms from A to B, two structures, and A satisfies phi, then also B satisfies phi. And the classical homomorphism preservation result is the one by Walsh, Linder, and Tusky, which says that the first order sentence phi is preserved under homomorphisms if and only if it is equivalent to an existential positive sentence psi. And then there are other results as well for preservation under injective homomorphisms or surjective homomorphisms and so forth. And this is the prototypical one. Right, so how would you prove such a result? Well, typically it's presented as a fairly straightforward consequence of the compactness theorem for first-order logic. The point is that this approach is not effective if you want to determine to which extent the complexity of a sentence is preserved. So if you start from a sentence phi, and which is preserved under homomorphisms, we know that it must be equivalent to some existential positive sentence psi. So how do you know if the complexity of the sentence is preserved? Somehow, if you apply the compactness theorem, you lose control over your sentence. You can mean many things by complexity of a sentence. For instance, you could measure the complexity of a sentence in terms of its quantifier rank. And if you do so, then there's a very nice result by Rossmann, which says that you can actually preserve the quantifier rank of a sentence, which is preserved under homomorphisms. So more precisely, a first-order sentence of quantifier rank at most K is preserved under homomorphisms if and only if it is equivalent to an existential positive one, again with quantifier rank at most K. So this result is called the equirank homomorphism preservation theorem, As a side remark, this is actually just the first step in the proof of a celebrated result by Rossmann, known as the finite homomorphism preservation theorem, which answered the problem which remained open for a number of years. So the problem was whether the classical homomorphism preservation theorem can be relativized to finite structures. And in fact, it turns out to be the case. And the proof is very involved. It's very combinatorial. And by the way, it's not comparable with the classical homomorphism preservation theorem because both the assumption and the conclusion are weaker. Okay? But so the kind of results I'm interested in, they are kind of these results. So equiresource homomorphism preservation theorems. That's what I'm interested in here. And if you want to at least be able to phrase such a statement in a categorical framework, you should be able to talk about model classes, so categories of models for a sentence, right? That's a necessary ingredient. What you can do, and let's do this concretely, you take a resource index above adjunction between a category of sigma structures and some above a category C. And then we will replace the sigma structures by some base category E. Okay, so if you're in this situation and you know that K bisimilarity coincides with equivalence in some finite logic fragment LK, then it's very easy to see that a full subcategory D of sigma structures is the category of models for some sentence phi in LK, if and only if it is saturated under K bisimilarity. It's essentially a very well-known fact in model theory and finite model theory, just cast in a more categorical way. You can do something similar for sublattices of FO. So we drop complements, so we allow ourselves to consider, for instance, existential positive sentences and things like that. If the K homomorphism relation corresponds to preservation of LK, then a full subcategory D of sigma structures is the model category, model class of some sentence psi in LK, if and only if D is upwards closed with respect to K homomorphism. And so this is just to justify the interest in saturation under K bisimilarity and upward closure with respect to K homomorphism. Now, if you forget about the concrete case of sigma structures, you can write down a statement, and this statement HP, which makes sense whenever you have a resource index above adjunction between some category E, here I'm calling it extensional category, but it's just some category E and a resource index above a category. And the statement says that for K and for full subcategories D of E that are saturated under K bisimilarity, D is closed under morphisms, if and only if it is upwards closed with respect to K homomorphisms. In the case of the Ehrenfeucht-Fraissé resource index above adjunction, this statement is precisely the statement of Rossmann's equirank HPT, just stated in a categorical way. And then you can strengthen this HP statement by replacing K bisimilarity with K isomorphism. Right? You obtain a stronger statement HP sharp here. Something that should be pointed out here is that the if parts in both statements, they always hold. So the interesting part is the only if one. Okay, so I'll try to be quick. Now we want to find sufficient conditions for this property HP to hold in a category, given some resource index above adjunction. And one such condition is the so-called bisimilar companion property, which says that for any object A and any positive integer K, A is K bisimilar to GK of A. Right? If you have this, then you get the HP property right away. And the proof is just 3 lines, and I can show it to you. So you start with the full subcategory D of E, and by assumption, this is saturated under K bisimilarity and closed under morphisms. And you want to prove that it's upwards closed with respect to K homomorphism. That means that if you suppose that there exists a K homomorphism from A to B, and A is in D, we must show that B is also in D. So by the bisimilar companion property, A is K bisimilar to GK of A. And then you can show it follows almost from the definition, well, really follows from the definition that the existence of a K-morphism from A to B, that's equivalent to existence of a real homomorphism from GK of A to B. Now, by assumption A was in D, by the bisimilar companion property, by the fact that D is saturated under K bisimilarity, GK of A is also in D, but since D is closed under morphisms, B is also in D, and you're done. And this can be applied, for instance, to a family of comonads that I haven't talked about. These are the guarded comonads that capture some guarded fragments of first-order logic. And you obtain equivalent source homomorphism preservation theorems for this logic. As far as we know, these are new results. I don't want to get into the details here. What I want to do next is just to look at the strengthening of the bisimilar companion property, which is the familiar notion of idempotent comonad, essentially. So you say that the resource index above adjunction is idempotent if all the induced comonads GK on the base category are idempotent. And in this case, what you get is that idempotency implies the stronger property HP sharp. And the proof is essentially the same as before. What you need to observe is that idempotency implies that for any object A is K isomorphic to GK of A. Okay, so not only K bisimilar, but actually K isomorphic. And then you can repeat the same proof as before, and you get the this proposition here. And this applies, for instance, to the model comonads on point encrypted structures. These are idempotent, and what this gives you is actually an equidepth homomorphism preservation theorem, not only for modal logic, but also for graded modal logic. So you can add graded modalities and that say that there exist at least n successors satisfying a certain property. And again, as far as we know, these are new results. Right. How much time do I have left?
So technically 3 minutes, but then there's 15 minutes of question time. So you can eat into that, but then there's going to be less time for questions.
Okay. I think I'll take 5 more minutes. I'll be very quick, just so this is perhaps the most interesting and involved part when it comes to homomorphism preservation theorem. So I feel I should say something about this. So there are some very tame cases like guarded fragments of just the logic or model logics where you have the bisimilar companion property and sometimes even idempotency. Okay, and in those cases, everything works very nicely. And then you basically have everything else. So these wild jungle of logics and comonads which do not satisfy this bisimilar companion property. So the question is whether you can actually force it somehow. And the idea comes from the work of Rosman. So this picture here is when you do have the bisimilar companion property, because then you can put this K bisimilarity relation in here, and you can conclude very easily that if A is in the subcategory D, then so is B. If you don't have K bisimilarity here, we can always put a K homomorphism equivalence here. You have K homomorphisms in both directions. And then you can try to look for objects A star and GK A star, some extensions of A and GK of A, that are homomorphism equivalent to the corresponding objects and such that you have K bisimilarity here. If you can do this, and then instead of chasing the diagram this way, you can actually go this way around and conclude that if A is in D, then so is B. The problem then becomes to show that you can construct these K extendable covers of the objects A and GK of A. And this can be done in the axiomatic framework, but you need to add some assumptions, some axioms on the base category and also on the adjunctions. I want to show you the axioms for the extensional category because they should look quite familiar. So the first axiom says that the base category has all finite limits and small colimits. Okay. And then the second one says that there exists a proper factorization system satisfying several stability conditions. And these are essentially the condition for an adhesive category. Okay, but instead of monomorphisms, we have embeddings here. The category sigma structures, of course, satisfies all these conditions, and so do pointed sigma structures. In fact, all the conditions in E1 and E2 are stable under technical slices. So it is very well behaved categorically. And then there's a bunch of conditions on the adjunctions that I'm not going to discuss, but they're not too nasty. The punchline here is that if you have a resource index above adjunction that satisfies all of these conditions, then you can build these k-extendable covers for any object A. And therefore, and this is the main result, you have the property HP. Now, a few words about the applicability of this result. So, of course, if you apply this corollary to the Ehrenfeucht-Fraissé resource index above adjunctions, you get back the equivalent HPT, which was proved by Rosman. Something more that you can get here is a relativization of this result to various full subcategories. So something which is quite difficult with these homomorphism preservation theorems is that when you have proved such a theorem for a class of structures, it's very difficult to relativize the theorem for a subclass. There are some sufficient conditions, but they're very weak. So what we get here from the categorical framework are some nicer and useful conditions, sufficient conditions for the HP result to relativize. So as soon as the comonad restricts to the full subcategory, you get a relativization of this HPT, and there are also some other things you can actually say. I should also point out that it seems that these axioms are quite specific to EK in the sense that other comonads do not satisfy them. So the hybrid comonad, I haven't discussed this, but it's a comonad for hybrid logic. It doesn't satisfy one of the axioms. And also, if you look at the Pebbling comonad, they do not satisfy one of the axioms. So in a sense, we're still waiting for new examples of gain comonads that do satisfy these axioms, because then you will get a homomorphism preservation theorem in the equiresource one in sort of automatic way. And I should say that in terms of the base category, so these axioms here, everything works nicely. So when things fail, it's typically concerning these four axioms that involve the adjunctions. But yeah, I'll stop here. Thank you very much for your attention.
Okay, thank you. Thank you. Again, I see some virtual applause happening. Very good. Who has some questions or comments for Luca? Please feel free to unmute yourself.
I have I think a very naive question.
Please go ahead.
It's about the definition of arboreal category. It's the property about the quotients that when you have a commuting triangle, then like if the diagonal is a quotient, then so is the first one.
Yeah, the sequence. This sequence.
Right.
Yeah.
So if I'm not mistaken, that amounts to say that the quotient satisfy the 2 out of 3 property.
Yeah, that's exactly the case. Yes.
And in my experience, that's a property that you want to, that you require on classes of arrows that you would like to regard as equivalences of some kind.
Yeah.
Does that make sense in this framework as well?
Yeah. So I'm not sure. I've tried to understand this 2 out of 3 property as pointing direction of model categories, but I think there is something to say there. But Yeah, so there is something here. So something which doesn't hold in any Arboreal category, but it's the case in all our examples, is that any morphism between two parts is actually a monomorphism. That's because the forest morphisms between parts, they are very rigid, so they have to preserve the height of points. So they cannot collapse any 2 points on the same branch. So if the domain is a chain, there is no way you can actually be non-injective. So you're always injective, and therefore, if you are a quotient, in examples, you're also subjective. So you're essentially bijection. The point is that it's a bijection which preserves the evaluation symbols but doesn't reflect them. So it's a an epimono, which is not ISO. I don't know if you would really want to see these as isomorphisms in a sense. But yeah, there's definitely something about these that points in that direction, but I haven't been able to really pinpoint to something concrete.
Okay, well, that's still an interesting answer. Thank you.
Thank you.
All right, thanks. Any more questions or comments? Okay, if not, let's thank our speaker again, actually both of our speakers. And let me end the recording here. You can stay in the conversation for more casual chat.
Sure.